Okay, so yes, first I'd like to thank the organizer for the invitation. So today I'm going to talk about curves on surfaces. So this is a joint work with Hugo Parlier. So let me first start by an introduction. So for today's talk, I will only consider surface sigma, which is a closed oriented surface of genus at least 2. So things may also be extended to a surface with boundary case, but this will make something more complicated. So to simplify the situation, I will only consider closed surface case. And so what do I mean by a curve? So this is the image of a continuous map from S1 to the surface. So, so here I just simply call it a curve, but you should think like a closed curve. And so one remark is because we will see everything from the topological point of view, which means, so first, I will consider all the curve up to homotopy. And secondly, so I will not consider the curve which is homotopically trivial. So so homotopically. So let me start by drawing some picture. So this is the genus 4 surface, and yes, okay. So a curve, simply you can think this is the curve, and there's no intersection.
You are now muted.
Okay, and you can also have a curve which, oh, I use different color, which can go this way. So you can see there's self-intersection come in. And so what I mean by up to homotopy is if I have two curves which can be changed from one to the other by a homotopy of surface, I will consider them as the same curve. So basically it's a homotopy class of closed curves. And by homotopically trivial, you can think the curve which is like this. So when you can find a homotopy of the surface which retract the entire curve into a point. So in this case, this is homotopically trivial, which is something we don't want. Yes. Okay, so what's the question we want to consider? Actually, curves are elementary objects when we study surface. It appears in many different parts, like when we try to describe a structure on surface, we consider using simple curve cut the whole surface into elementary piece. Or if we consider a geodetic flow, we consider the closed orbit. So basically, we can approximate the geodetic flow by considering a sequence of closed orbit. So, but in order to use curve to study all these things, first we have to know how to describe a curve. we have infinite many curves on the surface. So how can we distinguish two curves? If I just draw two curves on the surface, how do we know whether they are the same? So this is the question we would like to investigate. So the first is how to describe a curve on the surface. So maybe we are lucky, then we can find a coordinate system. Or maybe we cannot do this, but we can consider a weaker version of the question, which means can we at least find a way to distinguish two curves? So how to distinguish is it possible to distinguish two curves? So there may be several possible tools we can use, but for today's talk, I will use the most straightforward idea by considering the so-called the intersections among curves. So we want to find a collection of curves. Once we find this collection of curves, we choose it and fix this collection. And then we try to consider all the other, given any curve, we try to consider the intersection of this curve with the curves in this collection and try to see whether this information are enough to determine the curve. So given any curve, consider, let me give name alpha. Consider I alpha gamma for gamma belong to this collection C. So we try to see whether we can find a collection such that this information is enough to determine the curve. And here, what I mean by intersection here, let me give a definition. So gamma 1, gamma 2 are two curves sigma. And we know they are the image of some, we just find a parameterization of these two curves by 2, such that the gamma 1 equals phi 1 S1, gamma 2 equals phi 2 S1. And let me denote this set, maybe I gamma 1, gamma 2, to be the couple of parameters such that phi 1 T1 equals phi 2 T2. And then the intersection between gamma 1 and gamma 2 simply is defined by taking the minimal among all the, so we count the cardinal of this set and then take the minimal among all possible sets. So let me denote gamma 1 prime, gamma 2 prime, such that gamma 1 prime homotopy to gamma 1 and gamma 2 prime homotopy to gamma 2. So we can move the gamma 1 and gamma 2 by homotopy and try to see which pair will give us the minimal of the set of the minimal cardinal. And this will be our intersection. And so one remark is we also want to use this intersection number for the same, so gamma 1 equals gamma 2. So one remark is if we do so, if gamma 1 equals gamma 2, then we can find a positive integer k such that I gamma 1. So let me use gamma. I gamma gamma equals 2 times k. And this is a little bit different from the usual way we think about self-intersection of a curve. If we consider a curve as Judith current, and then with the self-intersection will be only the k. And here we are kind of like considering the order of these two. So when there's only one self-intersection, you look on the picture, and this number will be 2k because you can move this curve a little bit, and then you consider them a different curve, and this is the minimum you can have 2, which is the twice of the usual self-intersection we consider. So let me. So by considering this self-intersection, actually we can classify all the curves as the following. So gamma is a k curve if I of gamma gamma equals 2k. So if you look at the picture of the gamma on the surface, you can only find the k double point. And but by our definition, the self-intersection is 2k. And in particular, gamma is simple if I gamma gamma is 0. So there is no self-intersection. And let me use this picture again as the example. So here the red curve will be simple. So the blue curve here, we can see there is so if I call this alpha, so alpha equals 6, but the k will be 3. So there are 3 intersection points, but our counting is give us number 6. So back to our question. We will start by considering a simple case where the only curve we consider are simple curves. So simple case. We always start by studying some simple case when we study a question. So here we will consider simple curves. And for this case, actually, the main problem is fully solved by considering the Den-Thurston coordinate for simple curve. So we will consider the Thurston coordinate for what's called simple multi curves. So this coordinate not only considering the simple curve, but also consider a collection of pairwise disjoint simple curves. So here by multi-curve, simple multi-curve is a collection of pairwise disjoint simple curves. And so it will be very helpful if we first review this definition of the Den-Thurston coordinate. So how can we find this collection of a curve? By considering intersection with the curve in this collection, we can determine all the simple multi-curves. So so the idea is still the same. So we try to cut the whole surface into elementary piece, and then try to look locally the information of each, given any curve. We try to look locally the information, the intersection or whatever, and then by combine all this information, we can we can determine this curve. And what we mean by elementary piece is a pair of points which topologically, it's a sphere with 3 boundaries. So let me draw the picture. We know that given each surface, actually we can find a way to decompose the entire surface into pair paths. So we have to choose a path decomposition of the surface. So let me also draw the picture at the same time. So for simplicity, I will just draw the most easy one. So I didn't draw the backside of this curve. And so once we have this path decomposition, we can enhance it into a path cylinder decomposition by considering a cylinder neighborhood of each path curve. So so what we are going to do is simply take a neighborhood of each curve. And the last thing we want to add in the picture is we want to add a neighborhood of a dual graph of this path decomposition. So let me call it a marked path cylinder decomposition. Let me use a different color to draw this picture. So maybe consider this is the dual graph. And then we can take a neighborhood of this dual graph, which can retract to this graph itself. So it will give us this one, and
You are now muted.
oh.
You are now unmuted.
Okay, so so this is the preparation for getting the coordinates, and then what we are going to do is, given any simple curve, we try to make the curve going through the this neighborhood of the dual graph as much as possible. And then we can use this information to describe the curve. So let me be more precise. What I mean by as much as possible. So in each path, when I consider this neighborhood, actually it cut out a hexagon. Topologically, a hexagon. And then I will only allow, given any curve, my curve can only have arcs connecting different boundaries. So one of the, all the intersection of any curve I chose with this path will only be a collection of such simple arcs. And when I look at the cylinder, so my my curve, I will put all the intersection with the boundary of cylinder on this segment. And then you may have, so the intersection between the arc and the cylinder will be one of the following types. So first, you may have some arcs winding around several times, or you may have something looks like this, so coming from one side and then coming back. And if you are lucky and the curve you choose is one of the Pence curve, then the curve will just be like this. So, so you can see, basically what we are asking is try to make sure any curve we are considering going transversely to each Pence, and then putting all the difficulty of tying the curve into the cylinder. So the cylinder information will determine whatever the information of the curve in the Pence. And once we have this, and we can just draw one example, try to see how the thing works. So here you can see once we have this kind of arc, we first have information which is the number intersect this boundary. So the number of arc transverse in this cylinder. So this is the intersection number, which is a positive integer. And secondly, we can fix one direction to be the positive direction. And the curve, if it's transversal in this cylinder, is either twist positively or negatively. So we can, again, get an integer, which may be positive or negative, maybe 0, which tells us how the transversal arc goes. And these two cases are kind of exceptional cases just for complexity. So once this happens, we just put a positive integer, 1 for each case appears. So, so if my curve look like this, no. Yes. This is first, and this is my second curve, and then I can have so let me write down get some space. So we can see for the intersection part, so this is, there are 3G minor 3 Pence curve. So here I get 1, here I get 2, and up here I get 1, and then below I get 1, 2, and this is 0 by our convention. So this is 2, and this is 0. So this number tells us the intersection between the curve we consider, the multi-curve with the this Pence decomposition. And then there are also no, let me just write here, maybe. And this one I will tell the twisting number. So it's still a 3G minus 3 copy. So the first, there's no twisting, 0, and then we will fix all this direction to be the positive. So this one will be positive 1. So this arc has twisting 1, this arc has no twisting. So this is twisting 1, and then twisting 0, twisting minus 1, and this is, by our convention, is 1, 0, this is 1, and 0, and 1. So in this way, we also have another 3G minus 3 coordinate. So in total, this will give us a map from the simple multi-curve space to Z to the 3G minus 3Z plus. So this is bigger or equal to 0 cross Z 3G minus 3. So the first part is intersection number, and the second part is the twisting number. And we know that basically if we have two simple curve, even two simple multi-curve, we only need to look at their coordinate. If it's the same, then we know they are the same curve. Otherwise, it's different. It's the coordinate system. And but so far, we are not only use intersection, it seems like we also use the twisting, but in fact, the twisting is also an intersection with, with this dual curve. You can see when we have this dual graph and when we make it into a neighborhood, it has the boundary which are all simple curve transverse to the path decomposition. So this twisting number can also be told by considering this, by adding this dual curve into the system. And of course, twisting is kind of like an orientation intersection. You want to tell either you go this way or go this way. So in order to tell the orientation, you can, moreover, adding another copy of each one, the image of each one of them under the then twist around the path curve. So in total, you can just use 2 boards. I think it's enough. So this collection for the simple curve, including first the path curve, and then, so this C will be first the union of path curve with the dual curve. Let me use maybe CP. And then we also have the then twist along the path curve of this CP. So by considering any, given any multi-curve and we consider their intersection with this collection of curves, then we can actually tell each one of them. So for this case, it's easy just going this way. And so now let's move on, go to see the next level of this question. So what if we allow the curve to have self-intersection? So curves with self-intersection. So the first thing you want to try naturally is just try to see, okay, now I have a then twist, a then surface coordinate. Can it also work for this case? So the question is, does then surface coordinate work in this case? And the answer is no. And I will convince you by using the following example. So I will draw 2 curves, and they will have the same coordinate. So let me still consider this genus 4. Okay, I have to be careful. This is my first curve, I call it alpha. And then my second curve, so this is my beta. So my claim is the following. So fact one, alpha and the beta will have the same then certain coordinate. If we just naively extend the coordinate, and then they will have the same number, because you can see here, the only difference is here you have a parallel and here you have a cross. So it doesn't change the intersection with the cylinder curve, and it doesn't change the twist number. So they will have the same coordinate. And secondly, so you can see the insertion coordinate depends on the choice of simple curves. So path decomposition and also a dual graph of the path decomposition. So you may be wondering, what if I change it to another path decomposition? And the answer is still no. So in fact, for any gamma simple, you can show the I of alpha gamma equals I of beta gamma. So these two curves will intersect any simple curve the same number of times. So in this way, you can see if I only want to use a simple curve, I cannot tell alpha and beta apart from each other by considering intersections. So it seems that when we consider so it seems there is some obstruction when we try to generalize in this way. So so basically, the joint work with Hugo is about studying this obstruction. And ideally, if we understand very well this obstruction, we'll be able to find a way to tell any pair of curve on the surface. So let me see some more words on the obstruction we have here. So so we will give them a name. So let alpha and beta be two curves on sigma, and we say alpha and beta are zero equivalent if for any gamma simple, we have I alpha gamma equals I beta gamma. And we can generalize this definition by considering not a simple curve but a k-curve, and in this way, we get other equivalence relation between alpha and beta. So alpha and beta are k-equivalent if for any gamma which is a k-curve, we have I alpha and gamma equals I beta and gamma. So what does this mean? Basically it means when we cannot tell alpha and beta from each other by their intersection with a simple curve, we say they are zero equivalent. If we cannot tell them apart from each other by their intersection with a k-curve, we call them k-equivalence. So of course, once you have a definition, the first thing you want to check is, do they exist? And here I draw you a picture to show you zero equivalence exists. And in fact, once you understand why this gives you zero equivalence, you can also generalize it to show the k-equivalence also exists. So, so with this, we can actually state our main theorem, which concerns the relation among all these equivalence relations. So the theorem is the following. So first is, yes. So for any k, let me use a notation. If they are zero equivalence, I just put 0 under this. And then k equivalent. So this is just a notation. So for any k, a positive integer, if alpha and beta are k equivalent, this implies they are zero equivalent. And secondly, for any k prime, to distinct positive integer, no, strictly positive integer. So there exists alpha and beta such that alpha is k equivalent to beta, but not k prime equivalence. And
So you mean in the first one that if there is a k, for which that k equivalent, then there are zeros?
yeah, I showed C if then. So for any k, if this happens, then that happens. And here is for any pair, we can find the two curves such that this happens. And there are also curves alpha prime, beta prime, such that they are k and equivalence and k prime equivalence. And the third one is, so this is kind of only study locally k and k prime. And but in general, if I get any pair of curve alpha and beta non-homotopic to each other, we can always find infinitely many k's such that alpha and beta are not k equivalent. Oh, here it's not, yes. For that k. So, so let me make some comments on the three statements. So, yes. So the first one actually tells us, suppose I have two curves which cannot be distinguished by only considering k curves, then I will also fail when I only use simple curves. So immediate consequence. So let me use ck to denote all the k curves. So one, if ck cannot detect the two curves, this means C0 also cannot detect these two curves either. And secondly, so this seems like a good start point. And then we also want to see, okay, if I consider 1 and 2, do I also have this kind of, if 2 is bigger than 1, I can also have this kind of thing, but in general, no. So once you're considering k equivalence with k non-zero, then all the equivalence relation kind of like not coincide with each other. There's no one is stronger than the other. Basically, this is what the second one tells you. So, so you can find curves with k equivalent, not k prime equivalent, but you can also find a curve which is k and k prime equivalent. And the third one is, so the second one seems to be a bad news, but the third one is a good news. So in some sense, that means if I have alpha and beta are different, so a priori we can always find a k. It's just maybe at first we don't know which k, but there will be a k. We can tell them apart from each other. So so this is the main theorem and some comments. And let me come back to this picture. So so in fact, all the proof seems more or less related to what I will explain later. So basically, you can think some baby example where, let me, so if you consider this, this curve and this figure 8, you want to tell them apart from each other by considering intersection. So what you are going to consider is you want to include this part of the arc inside in the curves. So later you may be closing this way or you may be closing in the other way. It doesn't matter. So once you have this curve, you can you at least have like say one. So you will intersect these two curves differently. And these two curves actually you can think as when you take the finite cover, you will go to this situation. So what happens is in this curve, you can think I have this, and I have this picture. So in order to distinguish them, I must cross in the middle and following this two segment in each curve. But what if this part have self-intersection? Then the curve in the middle. So if these two white curve will have self-intersection, then this red curve must also have self-intersection. So in order to tell them it's kind of like you are holding by two big guys, and then these two big guys turn right, you should also turn right. And when they coming back, you should also coming back. And in this way, that means, so any curve can tell this intersection point will at least have one self-intersection here, which means if you take any simple curve, you cannot tell them apart from each other. And when you have this idea, then you know how to construct a more general example, right? So you just make you just make the picture to be more complicated to force all the arcs which can tell this intersection point to intersect more. Like if, for example, if I consider this part to have look like this, and the blue one also I change it to so this actually you can construct one example which is not one equivalent, because whatever the curve used to tell the difference, it will be something. Let's say intersect this part differently in the two curves, which tells us this curve must have at least two intersection points. That means you cannot tell them apart from each other by only one self-intersection. So so this is what happens, so there's one k-lemma we use by making the argument is a picture something similar to the picture for the insertion coordinate. So which we call the Pence lemma. So this is the which is kind of like try to tell a general picture for so how to draw a curve with self-intersection. So that means for any curve alpha, so there exists a marked Pence cylinder decomposition such that. So the first thing is in each Pence, you will have the same thing happen for the insertion coordinate. So the intersection will only be simple arcs connecting different boundaries. And secondly, in each cylinder, what you will have is you can think the picture will look like you have a bunch of simple disjoint ones, then you add a crossing in it. So your intersection point will be on here, and all the arcs will be either twisting 0 or twisting 1, so either this way or this way. And each pair of arcs will only intersect once, so basically it's the same as saying they are twisting either 0 or 1. So this will be what you will see in this decomposition. And so you can see by this picture, we can formally think the curve with self-intersection coming from two information. The one is you will have a base multi-simple curve, And secondly, you will have some combinatory information. Basically, in each cylinder, you will add some crossing. Let's say here, maybe at the beginning, you have a picture look like this, and then you add a crossing among the different arcs. And then the lemma simply is saying you can construct all the curve with self-intersection in this way. And if you're familiar with the train track, basically it's basically saying all the simple curve, all the curve with self-intersection can be carried by some of the train track. And this idea actually already appeared in a paper by Viveka and Huan, where so the title was counting hyperbolic, counting curves on hyperbolic surface, and it's let me just write this down. So this is some comments. So curves with self-intersection can be formally considered as simple multi-curves plus some crossings. And the crossing only add in the cylinder part. So this also appears in a paper by Viveka and Huan called Counting Curves in Hyperbolic Surfaces. So the advantage of this way is simply you can see when you try to count the growth, for example, you fix a k, you consider all the curve with k self-intersection, you want to know what's the growth rate of this kind of curve. So as you consider longer and longer curve, and how many of them have k self-intersection, and what's the relation between this number with length k. And this basically tells you, actually, there's not much difference from this and you're counting the simple one. So they will have the same growth rate, but with different coefficient. And this result already appeared in one of the Mazzucani's paper, but which use a different idea to prove it. So this is the first one. And the second one, back to our original question. So we want to know, is it possible to tell them apart from each other? So there is a good news. So the third part actually tells us here, we can always find some k to tell them apart each other. Actually, if we know more information about alpha beta, we can make the k to be more precise, which is the following. So you can show for any k. So there exists there exists a c bigger than 1, which is a constant, such that for any k in n, for any alpha and beta, with at most k self-intersection, there exists a k, let me use L smaller than c times k, such that alpha and beta are not L equivalent. So if you know alpha and beta have intersection at most k, then you don't need to test L equivalence for all the L go to infinity. You only need to make this L going to some multiple of k, and that's enough to tell the alpha and beta apart from each other. So this is the good news. But the bad news is, so once your alpha, sorry, thanks. And the bad news is once the alpha and the beta, you include a curve with self-intersection, it's no longer the same as in the simple case. Simple case, you only need to test the intersection with finitely many simple curve. But once you have self-intersection, you always have to test infinite many. So this is once curves with self-intersection. So we always have to test have to include infinite many curves in the we call it let's say the testing collection, let's say. And why this is true? Basically, is you try to not only tell the simple, so it's still from the first one. So when you test this part, what's the simple multi-curve carrying this curve with self-intersection? You only need a finite many. But the crossing part, you need infinite. Basically, this part is kind of like you try to test the mapping class group element. So when you try to test the element in the mapping class group, you need for each element, you need something to test. So this makes this collection to be infinite instead of only finite many for the simple case. So this is the second comment. And the third comment is you can also extend everything to the surface with boundary. And the only thing additional you have to tell is about what happens if this is your boundary and you have some part of the curve twisting around the boundary. And this is some additional information you have to test. And let's see, and the last one is actually the whole story can be generalized to the space of currents. So basically, what we can say is the following. So the following is, so suppose C is geodesic currents on the surface with a certain property. You can always define an equivalence relation for currents. So when your C1, C2 are two currents, we say C1 is equivalence with C2 with respect to C, if and only if for any C in this set. I should make it. We have the intersection between the C1 and C equals the C2 and C. And if we look what we have done before, the k-equivalence simply means here we are considering all the currents coming from curve with the self-intersection k times. And C1 and C2 we consider are the current coming from a curve on the surface. And but we can also replace C in this case by, for example, we consider the currents, the Liouville currents for the surface. Basically, we are considering the entire Teichmüller space. And we ask if two curves, the current coming from two curves, whether they are equivalence with respect to this. And this actually gives us another equivalence relation called a length equivalence relation. Basically means the two curves are length equivalence if and only if for any hyperbolic metric they have the same length. And these two exist, and I can show you one example. You can think why, as an exercise, why this is the case. So this is the first part. So these two curves will be in the same pans in the surface, and no, not here. So actually, it's not difficult to see why this is true, because these two curves actually are different by a symmetry of these pens, right? You exchange the two, you can't, whenever you have a hyperbolic pair of pens, you can always cut into two isometric hexagons, and exchanging these two things will give you an orientation reversing isometry of the pens, but this will send one curve to another. So they will always have the same length. And of course, you can consider more general currents and more general property for the current. Okay, I think I will stop here. Thank you very much.
So, do we have a question? Yes.
Yes.
I want to do something stupid and test with all prime numbers. And if I cannot detect them with all prime numbers, does it mean it's true that they are homotopic or not?
So how would you describe these prime numbers in terms of curve? Like
The K are all prime.
Yeah, sure. Okay. So so basically, it's something like when we have two curves k equivalence for some k, how big this k can, the set of k can be, and yes. So far what we know is given any finite number of k, we can construct two curves have k equivalence for any such k. But we don't know yet. We don't know yet whether you can do this for infinite many k's. So that's one. So I mean, at first you may think, okay, so if I have a k go to infinite, a priori I should have two curve length equivalence because normally you think you will have a sequence of curve which a priori will be equidistributed on the surface, which give you the convergence of lengths to be the same. But in fact, this is not the case because I don't know whether this is true because when we see the sequence of curve which is equidistributed, we don't know which k this sequence hit. So you have a sequence of curve which equidistributed in all the metric. I mean, in the Jolita flow, you don't know which sequence of k you hit in this sequence. So that's why I cannot see anything when your k have infinite. But there are always examples for finite many k. So you can make your, yeah.